I will teach, and I am here today to teach you some barycentric coordinates. So barycentric coordinates are a bashing technique in Olympiad geometry. They're usually based on areas, and they're very useful for a lot of problems. If you don't think bashing is morally correct, then maybe what you can take out of it is like techniques involving areas that can be useful to solve problems and similar things. So what are barycentric coordinates? What you do is that you have some triangle, ABC, and this will be our reference triangle, A, B, C. And the reason that we have because we have a reference triangle, ABC, barycentric coordinates is very applicable to a lot of problems, because most geometry problems start with let ABC be a triangle, and then they define a bunch of points. So usually you let ABC be a reference triangle, you find the barycentric coordinates of the million points they give you, and then you can prove some desired property. And if you have some point P anywhere in the plane, P, then the barycentric coordinates x, y, z of P, coordinates x, y, z of P, can be found in two equivalent ways. Number one is such that the vector P is equal to x times the vector A plus y times the vector B plus z times the vector C, and x plus y plus z equals 1. Here the origin is taken to be whatever point not on the sides of the triangle. And equivalently, x is going to be the area PBC over the area of ABC. Y is going to be the area of APC over the area of ABC. And Z is going to be the area of ABP over ABC. Okay. Here, it's important to note that these areas are taken to be signed. ABC, signed area. Now, what does it mean for the area to be signed? This means that we have by convention that if the order of the vertices is counterclockwise, like in this case, the area is positive. However, if the order of the vertices were clockwise, say we name this ACB, then the area will be negative. So this will be negative ABC. If we have this, then what I have written above about x, y, and z is true. And besides, it's really convenient. Why? If you look at P, if A and P are on the same side of line BC, then ABC and PBC will have the same sign. A and P, same side of BC. On the other hand, if they're on opposite sides, say P was like here, ABC, in this case, would go counterclockwise, but PBC would go clockwise. So ABC and PBC have different signs. When A opposite side of BC than P. Okay. This is just an interesting observation, which is that this tells you when a point is on the inside of the triangle, given their barycentric coordinates. Particular, P equals XYZ is inside ABC. So triangle ABC. If and only if X, Y, and Z are greater than 0. And this just means that P is on the same side of BC as A, so it's over here. It's over here. It's on the same side of AC as B, so it's over here. And it's on the same side of AB as C, so it's over here. And you can check that the intersection of those three areas is simply the triangle ABC. Zero. Now, we can easily calculate the barycentric coordinates of some points. In particular, we can easily find that A will be 1, 0, 0, B will be 0, 1, 0, and C will be 0, 0, 1. Now, what we've just done. If M is the midpoint of side BC, what are the barycentric coordinates of M? I'll let you think about it for a second.
Zero half.
Sorry? Zero?
Half.
Yes, that is correct. Now, in case you don't see this, the idea is the area of MBC is 0 because M is on side BC. The area of AMC is 1/2 of the area of ABC, precisely because M is a midpoint. And you can either see that this area is also 1/2, or you can just argue that since they add to 1, the other one must be 1/2. So. And similarly for the other midpoints, the position of the 0 will just switch around based on which midpoint it is. Now, most of the power of barycentric coordinates comes from the following formula, which I'll not prove because it's long and tedious and no one wants to see the proof. But if you're interested, you can look it up. We have points P1, P2, P3 with barycentric coordinates xi, yi, zi respectively. In particular, P1 has x1, y1, z1, P2 has x2, y2, z2, etc. Then the signed area of P1, P2, P3 is given by the determinant. Oh, sorry. The signed area of P1, P2, P3. If you take Z with Ceva, I'll go back. This is just by convention, like here. If we look at this. X, Y, and Z aren't like coordinate axes. These are just variable names. As in, if say my vector were here, then if this is A, then I'm doing some X part of the way to A. Then if this is B, I'm doing some Y part of the way to B. And then if this is C, then you go some Z part of the way to C. And when you add these, you get P. Now here, back to this. The signed area of P1, P2, P3 divided by the signed area of ABC is given by the determinant of the 3x3 matrix. X1, Y1, Z1, X2, Y2, Z2, X3, Y3, Z3. Some examples which may convince you that this is true. If we choose P1 equals A, P2 equals B, P3 equals C, and we get 1 equals the area of ABC over the area of ABC equals the determinant of 1, 0, 0, 0, 1, 0, 0, 0, 1. You may recognize this as identity matrix. Determinant is just 1. And this is true, which is good, because if it weren't, we'd be really scared. If you look at triangle AMC, for example, half equals the signed area of AMC over the area. Actually, I'll do an example to show the signs. You can say negative 1/2 will be the area of CMA divided by the signed area of ABC, which will be the determinant. C is 0, 1, 1, sorry, 0, 0, 1. M is 0, 1/2, 1/2. And A is 1, 0, 0. And so if you look at this determinant, I'll calculate it by expanding by binaries down this row. So we just get that this is 1 times the determinant 0, 1, 1/2, 1/2. And this determinant you can easily see is negative 1/2. And again, the signs all check out. Any questions thus far? Nope. Okay, cool. Now then, we'll see what are the things we can derive from this area formula. Imagine that P1, P2, and P3 are collinear. Then the signed area of P1, P2, P3 equals 0. Hence, when we use this area formula, you'll know that this determinant x1, y1, z1, x2, y2, z2, x3, y3, z3 will equal 0. We can use this to derive the equation of a line. We do it as follows. Suppose you have point P with barycentric coordinates. What should I call it? Oh, it's 5. This one's Y1, Z1. And you have point Q with barycentric coordinates x2, y2, z2. And you want to find the equation of line PQ. Well, suppose you have some point x in the line. And x has just general Barycentric coordinates x, y, z. Then we know that x, y, z, x1, y1, z1, x2, y2, z2 equals 0. And now if we expand this determinant using expanding by minors to this row, you see that x times this determinant minus y times this z times this now these determinants here are just constants, which I'll call u minus v and w. I call this one minus v so that it cancels with this negative. I can just write that the equation of a line is of the form ux plus vy plus wz equals 0. And if you notice, u, v, and w aren't unique. I can scale this by 2 and say, for example, 2u plus 2v plus 2wz equals 0. That's fine. There's no problem with that. These constants don't have to be unique. It's just that once you have u, v, and w, or like any example of u, v, and w, if you stick with it, then this equation will just hold for any point on the line, and only if the point is on the line, because of the above procedure. So, for example, if you wanted a point on the diagonal, on the line passing through A, line passing through A, well, we know that A, which is the point 1, 0, 0, lies on the line. So if we substitute in here, we get u times 1 plus v times 0 plus w times 0 equals 0. So u equals 0. In other words, lines passing through A will have equation vw plus wz equals 0. And if you know another point on the line, then you can just find this. In particular, for any point on the line, you will have that, okay, so I do vy equals negative wz, and then I divide vy over z equals negative w, like this, y over z equals negative w over v. This is true for any points on the line through A, except A because the z coordinate is 0. Except A. What this is saying is, if I have some point x, y, z. If I don't care about this, the ratio of these will always remain the same. So we can do a neat little trick to express this more concisely. And for that, I will introduce non-homogeneous barycentric coordinates. And for this, what you do basically is you say that the barycentric coordinates kx along ky along kz equal normal barycentric coordinates x, y, z, where x plus y plus z equals 1, which is important because these have to add to 1 for example, the area formula to work. And k is just some non-zero constant. Now, the benefit of working with these homogeneous coordinates is that usually they're easier to deal with, easier to compute with, because if your variables add to 1, usually you'll have a lot of fractions, like 1/2, for example. And there are cases where you don't need the condition that x plus y plus z equals 1, and it's fine to just plug in kx, ky, kz for a suitable constant k. Now, if you're not sure which one of the two you should use this one, even if it's horrible, because this one is guaranteed to be correct. If you use the other one, it may be false. For example, in the area formula, you have to use x comma y comma z, the ones where the variables add to 1. Because if not, you're going to get some multiple of the area. And then that's not very useful. However, when the area is equal to 0, having some multiple of the area is still the area. So in this case, it doesn't matter if you use homogeneous or not homogeneous barycentric coordinates. In particular, since the line equation is derived from when the area equals 0, you can see that this is a homogeneous expression in x, y, and z, and you can use homogeneous barycentric coordinates. In particular, you can plug in kx, ky, kz into this formula, and it'll still work. Indeed, this is what I was talking about earlier with multiplying constants here. It doesn't matter. The equation doesn't change. And I'll just look at these as being kx, ky, kz instead. And so with this in hand, notice that ky over kz equals y over z. And so what this equation is telling us is that the line passing through A will be characterized by all points that have some x coordinate, I'll call it t, and then the y and z coordinates are always in the same proportion. So that if my original point, like if the line passes through A and P, where P equals, I'll say x1, y1, z1, then we know that y over z will equal y1 over z1 always. So that this proportion, ky over kz, will also be y1, z1. And so what this is saying, this parametrization of the Cevian through A that passes through P, what it's saying is, homogenously, these two coordinates are always in the same proportion. And the first one doesn't matter. And the proportion they are in is the same proportion as the point that the line goes through. Yeah. And if you translate this into like non-homogeneous coordinates, you divide by t plus y1 plus z1 so that they all add to 1, and it's not very nice, but this is why we like homogeneous coordinates. However, I would not be able to use these coordinates for the area formula, for example. Any questions about this homogeneous coordinate or areas? Okay. No. All right. So, for example, the equation of the median triangle ABC is M, the midpoint. Since we said M equals 0, half, half, which I can call homogeneously 0, 1, 1. Usually you don't need to say the colons. I'm just doing it to emphasize that these are different, because these don't add to 1. Generally, the coordinates don't add to 1. It's homogeneous. If they do, it's not. And then this line, AM, as well, you can say, you either call it Vy plus WZ equals 0, and then plugging in M, you see that V plus, V times 1 plus W times 1 equals 0, so V plus W equals 0, so W equals minus V. You just have Vy minus Vz equals 0. We don't care about the V, so we can just write Y equals Z. That's one way of expressing the equation of line AM. Or we can use our parametrization earlier. We know that this is T colon. What is the B coordinate of M? 1. What is the C coordinate of M? 1. And if you notice, these are really saying the same thing. That the ratio, the homogeneous coordinates are saying that the Y and Z coordinates are a ratio of Y of 1 to 1, i.e. that they are equal. Y equals Z. The equation of the line passing through both midpoints, call this N, midpoint of AC. What would this be? Well, we know the equation is ux plus vy plus wz equals 0. We know it passes through the points 0, 1, 1 and 1, 0, 1. Note that this is n, which unhomogenized would be half, 0, half. And so we plug this in. This is a v, by the way. So we plug this in, we have v plus w equals 0 and u plus w equals 0. So we can express everything in terms of w. V equals u equals minus w. So this is minus wx minus wv plus wz equals 0. We can cancel out the w's to have nicer constants. Minus x minus y plus z equals 0, or z equals x plus y. Now, some of you may realize, if you are on this medial line, what should your z coordinate? Well, if we draw this triangle, the area, the base of this triangle, sorry, is the same as the base of triangle ABC. But since you're half of the way there, this height, as opposed to this height, will be half the height. So if this is P in the medial line, you see that ABP over ABC equals 1/2. How can we see this here? Well, if we impose the condition that x plus y plus z equals 1, that is, we dehomogenize the coordinates, then x plus y equals 1 minus z, so z equals 1 minus z, which implies z equals 1/2. Cool. Now, with barycentric coordinates, we can prove several theorems. For example, we may prove Ceva's theorem. Remember A, B, C, have some point D and B, C. E and C, F, maybe. And Ceva's theorem says AD, BE, CF concur if and if and only if BD over DC times CE over EA times AF over FB equals 1. And so the idea here is, if you look at D, what are its barycentric coordinates? Since it's all in BC, the A coordinate is 0 and has some Y coordinate D. And then since they add to 1, the Z coordinate will be 1 minus D. Therefore, equation of line AD, as we saw before, is have Vy plus Wz equals 0, plug this in, Vd plus W1 minus D equals 0. So V equals minus W1 minus D over D. Hence, minus W1 minus D over D Y plus WZ equals 0. Again, remove this to make life simpler. And you just have Z equals 1 minus D over D times Y. This is equivalent, by the way, to the parametrization T D minus D. Similarly, we'll get that BE has equation 1 minus E over E X equals Z equals X, and CF has equation 1 minus F over F Y Z, sorry, I said all of them. 1 minus F over F X equals 1. Now, when does the system of equations have a solution? Well, we want this to, if we consider these three equations, the three lines intersect if there's a point x, y, z such that all of these three are true. That is, if the system of equations has a solution. So when does it have a solution? Well, if it has a solution, we know x equals 1 minus e over e times z, which is equal to 1 minus e over e, but z equals 1 minus d over d times y. But y equals 1 minus f over f times x. Now, x cannot be 0. Because if it were 0, then it would be a point on this line. And since it's in these two, it would have to be both b and c, which doesn't make sense. And so we can cancel this out and say what we need is 1 minus d over d times 1 minus e over e times 1 minus f over f to equal 1. But this is exactly what Ceva says. So if you looked at the triangle, the fact that the b coordinate is d is saying that this right here is d, and this is 1 minus d, and so forth. And thus, what this is saying is bd over dc times ce over ea times af over fb equals 1. And we're done. Similarly, you can prove Menelaus using this. Any questions thus far? All right. Let's see some special points then. I'll just copy this table. Have here. Okay. This is from Evan Chen's book. This table right here. I hope you can see why most of these are true. Most centroid is easy to see, since by properties of the centroid we know that the three areas from the centroid to the two of the vertices are the same, and they're a third of the triangle. So dehomogenized, this would be 1/3, 1/3, 1/3. But homogenized, it looks prettier, so we write 1, 1, 1. The in-center being ABC comes down to the angle bisector theorem, and that the in-center is somewhere here. It intersects here. This is A, this is B, this is C. This is B, this is C. This is A. Then we know, suppose this intersects at D. We know that D equals 0. Then let's call this D. No, call this D. So this is 1 minus D. 0, D, 1 minus D. By the angle bisector theorem, D over 1 minus D equals B over C. So this is 0, B, C. And then since I is on AD, and AD has parametrization T, B, C, you just have to find T. But then you do the same thing with the other angle bisector, and you see that I should have parametrization A, S, C. And then if you do the third angle bisector, it should be A, B, R. And you can easily find the point that satisfies all three of these. A, B, C. And so cool enough, what this is saying is that the areas from I to two of the vertices are in a ratio that's the same as the ratio to the sides. Now for the median point, the at center, etc., you can use similar tricks. I'll use as examples for you to try. If you get stuck, you can message me or something. And then for the orthocenter and the circumcenter, you use the area definition. And so, for example, for the circumcenter, these all are. This is 2A, this is 2B, it's 2C. And so the area of OBC over ABC will equal, well, the area of OBC is 1/2 R squared sine 2A over ABC. And similarly for the others. And so you'll get that this is 1/2 R squared sine 2A over ABC, comma, 1/2 R squared sine 2B over ABC, etc. And then we can just homogenize this by multiplying by ABC over 1/2 R squared to get that this is sine of 2A sine 2B sine 2C. And this is much nicer. Any questions? All right. Here's a problem for you to think about. Let P be a point with barycentric coordinates x, y, z. And actually, I'll do them like this. And none of these are 0. What none of these are 0 means is that it's not on the sides of the triangle. Okay. Show that the isogonal conjugate of P star has coordinates a squared over x, b squared over y, c squared over z, and the isotomic conjugate is 1 over x, 1 over y, over z. And this is from Evan Chen's book. So give this a try for a while.
What are isotomic conjugates and iso?
Okay, well, that is a good question. If you have a triangle ABC, You have a triangle ABC. Some point P here. This is a bad choice of P. I'll place it like here. And the isogonal conjugate is if you draw these lines, the Cevians through each point passing here. You have some angle here. One. So consider the line that makes the same angle but with the other side. Then you have here some other angle. Two. Consider the line here that makes the same angle but with the other side. I.e. the reflection across the angle bisector. And if you have this third line here, so 1, 2, 3. This one look quite straight. This is also 1, 2, 3. Then these three lines, which are the reflections of the angle bisector, intersect at a point, and this point is the isogonal conjugate. Now, isogonal, the name isogonal comes from equal angles. Iso is a prefix that means equal, as you can see in words like isomorphism, isogonal, isotopic, etc. And gono means angle. This is why trigonometry is like study the angles of a triangle, and polygons are called that because they have a lot of angles. Isotomic, on the other hand, means equal lengths, because atomic comes from length. So instead what you do is, in the same picture, in the same picture, instead of doing the equal angles, it seems I can't erase. Well, I'll just draw another triangle. A, B, C, some point P. I can draw these lines. Okay. Then you have this length here. What if you take the same length, but from point C, and consider this line? You have this length here. Do the same length from the other vertex here. You consider this line. I want to make it seem like these do not intersect in this. Oh, the problem here is I made this really close to the midpoint. So since this is really close to the midpoint, when I do this switching, it'll be like super close to P, like here or something. Yeah, it'll be like about here. It's super close. 2, 3. And that's why these look almost concurrent. But if P were farther away from the C median, then these would look farther away as well. And the intersection of these three, which also concur, is called the isotomic conjugate of P. And so with these definitions, you can prove this problem using barycentric coordinates techniques. We will discuss this at 11. And if you've solved it or want a hint or have a question, you can send me a message through the chat. I just realized I said at 11. That's my time zone. That in 2 minutes.
Okay, I have an idea. Shall I tell? for the isogonal conjugate?
Isotonic?
I have an idea for the isogonal conjugate.
What is your idea?
Yeah, so like in this diagram only, we can just use the aerial definition, right?
Sorry, the region what?
Oh, wait, no, that doesn't work. Ignore.
Okay. We can discuss this now. I feel like isotomic is the easier example to discuss first. So I'll do this first, then go to isogonal. So suppose this 7 AP intersects side BC at D and APT intersects at E. What do we know? We know that P has coordinates x by z. Therefore, AP has parametrization T, Y, Z. Now, D is on both line AP and on side BC. Since it's on side BC, its first coordinate is 0. So we know that D equals 0, Y, Z. Now, what does this tell us about E? If we call BDD and DC 1 minus D, we know that EC is D and BE is 1 minus D. So D has homogenized, dehomogenized coordinates 0, 1 minus DD, while E has coordinates 0, D, 1 minus D. What this is telling us is that we just switch the Y and Z coordinates for D to get E. Therefore, in this homogenized case, have E equals 0, Z, Y. Now, Cevian AE have parametrization S, Z, Y. We know that PT is on this Cevian, so we know that PT has this form. In much the same fashion, actually, I'll call this Q instead of P. I'll call this P. Much the same fashion, it also equals Z, Q, X, and it equals Y, X, R. By doing the same thing with the other two sides. Now we need all of these three to match up. How can we do that? Well, you know that Z, if we look at these two, you know that Z over Y equals Q over X. So Q equals XZ over Y. And if you look at the second one, then this tells you that it equals Z XZ over Y X, and dividing by XZ, which we can do because it's just multiplying by a constant, to have this equivalent homogeneous form. Z over XZ is 1 over X, XZ over XZ is 1 over Y, and X over XZ is 1 over Z. And this is what we want to prove. And so if you see, what we did was we had a triangle, we were given a point, and we wanted another point. So we found the coordinates of everything, and it just gave it to us. Because from this point you can get this one, which then gives you this one after some careful analysis, which then gives you some coordinates of this. You repeat for the other sides, and it works. For isogonal, you do basically the same thing, but you need an extra property that I maybe should have given to you. This is D, and this is E. Then, if you apply the extended angle bisector theorem, twice, you will obtain that BD over DC times BE over EC equals AB over AC all squared, which I'll write as C over B squared. So I probably should have given you this, but I forgot. So if you remember this, you can do the problem. I'm sorry. Yeah, so with this, you do the same trick as for isotonic. If this is D and this is 1 minus D, and if this is E and this is 1 minus E, then you have D over 1 minus D equals 1, times 1 minus E over E equals C over B all squared. And then D has coordinates 0, 1 minus DD. E has coordinates 0, E, 1 minus E. And so you do D equals 0, YZ as before. Then Y over Z equals 1 minus D over D, which equals 1 minus E over E times B over C squared. Now, this means E over 1 minus E equals B over C squared, Y over Z. So E equals 0, B squared Y. Wait, no, B squared is Z. B squared, B squared is Z, C squared Y. This over that. Oops, I have Z and Y the other way around. Should be right. Yeah. And so P star will be P star will be T, B squared Y, C squared Z. And after you find the equivalent forms for the other one, like from the other two sides, you can find, you'll get P star equals something not in this form, but you'll like divide by XYZ or something similar and get it in this way. So finally, to conclude, in this last 20 minutes, yes, we can solve some problems. I have some problems stolen from Evan Chen's book. Now you can read. Let's do this. I'll give you 5 minutes to think about it. If you solve it or have an idea, you can tell me in the chat or out loud. And in 5 minutes, we'll start discussing it. See how long that takes us and see how many problems we can do. Okay, let's try to handle this problem. So we're gonna say This is A, this is C, and this is B. No. Wait. Side CA is 10 beyond A. No, it's A. Wait, no. Okay. My bad. I apologize. So this will be BC. BC. Okay, so A, B, C. I'll have to move these a little so that it's like on. Make this line a bit longer. Okay, so D is on this line so that BC equals CD. So D is about here. This equals this. And E such that AE equals 2CA. So oops, E is very far away. I think what I can do. I'll just cheat. A is now here. Okay. And so E will be about here. A bit farther away, but whatever. And so EA is 2CA. Let's see, AD equals BE. Then this triangle is right angled. Now, two of these conditions look very easy to deal with what we have now. Turn machinery, CD equals BC. And AE equals 2CA. Why? Well, what are the barycentric coordinates of the point D? You know the A coordinate is 0 because it's on side BC. And look at the B coordinate. Well, here, this base is the same as BC, and the height for both triangles is the same. So the area is the same. Now it's not 1 because D and B are on opposite sides. The signed area will end up being -1. And then what if you look at the ABD? Well, the area, sorry, not the area, the base of both triangles, the triangles ADBC and ABD is the same, but the height of ABD is double the height of ABC since BC equals CD. Therefore, this is twice the other area. And as you can see, not all of XYZ are positive, so D is not inside the triangle. All right, similarly, we can find point E. Since it's on side AC, we know the second coordinate will be 0. If you look at EBC, since EC is 3 times AC, the height will be 3 times the height of ABC. And so this area will be 3 times as much. And if you look at ABE, then since this is double AC, this area will be double the area of ABC. But since E and C are on opposite sides of line AB, this will be -2. So this is really easy to deal with. And now we have the barycentric coordinates of all points. The problem is we may not know how to deal with final length of AD and BE. So for this, I'll go on a brief tangent on displacement vectors so that we can derive the distance formula. Recall that barycentric coordinates are just vectors. XA plus YB plus Z plus ZC. So I'll call this 1, 1, 1, U, X2A, plus y2b plus z2c. And so as we can treat them as vectors, we can consider a displacement vector, which like translates us from one point to the other. So we call the displacement vector PQ, displacement vector. This will equal x2 minus x1 a, y2 minus y1 b, z2 minus z1 c. And I will abbreviate this by calling this big X, this is big Y, and this is big Z. And if you notice, in a displacement vector, PQ, with coordinates X, Y, Z, its coordinates don't add to 1, they add to 0. Now, this can be useful for a myriad of reasons. The one we'll see right now is for the distance formula. So suppose you have a displacement vector PQ that's equal to big X, big Y, big Z. And so what we'll do, so that this equals X, A plus Y, B plus Z. See? What we'll do is we will translate the circumcenter to the 0 vector. So that all our vectors are with the circumcenter equal to the 0 vector. That way, this length, all these vectors have the same magnitude. Then the length of PQ squared, I don't know why I used absolute values, this is just the side length. PQ squared will equal PQ dot PQ from vector algebra. And this is XA plus YB plus CZ dot itself and if you dot this out and you do all the necessary computations, which I will skim over because in the interest of time, you use at some point that X plus Y plus Z equals 0. So you do this, blah, 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 and you get that this is equal to minus A squared YZ minus B squared ZX minus C squared XY, where A, B, and C are the sides of the triangle, as you should. And so with this distance formula, which importantly, we can use it here. For AD, for example, AD squared will equal first we find the displacement vector AD. This will be equal to, since A is 1, 0, 0, this is 0 minus 1, minus 1, minus 1 minus 0, 2 minus 0. And similarly, the displacement vector BE will be, since B is 0, 1, 0, 3 minus 0, 0 minus 1, minus 2 minus 0. So these are the displacement vectors. So AD squared will equal negative A squared times negative 1, negative 2, minus B squared times minus 1, 2. Also, this is not negative 2, this is minus C squared, negative 1, negative 1. That is 2A squared plus 2B squared minus C squared. BE squared will equal minus a squared times minus 1 times minus 2 minus b squared times 3 times minus 2 minus c squared times 3 times minus 1, which equals minus 2a squared plus 6b squared plus 3c squared. Now, since AD equals BE, this implies 2a squared plus 2b squared minus c squared equals minus 2a squared plus 6b squared plus 3c squared. So that 4a squared equals 4b squared plus 4c squared. We divide by 4, a squared equals b squared plus c squared, which from Pythagoras implies the angle A is 90. Weird. Any questions? Okay. This class was just a super brief introduction to barycentric coordinates. There's a lot that you can do with this. You can find perpendiculars, you can find the equation of a circle, you can find the power of a point with respect to a circle. You can intersect lines, you can have points at infinity. The power of barycentric coordinates is vast. And here we covered just the basics, and we went a bit into displacement vectors. So if you're interested in learning more barycentric coordinates, you can either read up on them in Evan Chen's book, or he has a really useful handout. It's called Bary Full. I believe you can find it online. And otherwise, you can just send me a direct message in Discord or send me an email, which I maybe will respond. And you can become, exactly, you can become a seasoned Bary basher like myself and Pratt. And enjoy life, not thinking about some geometry problems.
Thanks for the class. I'll stop recording.